Okay, E6 glass. This one is about glass, and we follow the same outline: the properties, production, and application for the material. It's a nice material. It's transparent. It allows light to be transmitted, which makes it interesting for us as architects for the functionality of the building. And it has some, say, technical issues of the material itself, which makes it interesting for the engineers. It's said that was identified to be a material around 50 BC. The story behind this sand was actually boiled by fire, ending up in this black pearls of glass. Then later was developed through a process to be used as a material for yeah, pottery like products, and by that was seen as a material it could be used for construction later, but it actually took 1,000 years to get this process of the manufacturing developed so that it was possible to be used. It's an amorphous isotropic material. It's actually a liquid. That's how we always explain it. It's not a solid material, it's a liquid in the process of hardening. Due to our average temperature, this process of hardening is taking forever, ages. There's always the story of being able to see this process of flowing of glass, which I have to say I don't believe, because the process is so long, takes 10,000 of years, so we will not I'd be able to identify this as an opportunity. The properties shown here: the density is quite high, the compressive strengths are theoretically quite high, the tensile strengths are theoretically quite high, but due to the surface being a liquid, scratches on the surface actually tend to break the material itself. So by a scratch on the surface, the material itself is not having any tensile strength anymore, and that brings us to this failure without any warning. So if a glass piece breaks because of tensile strength, it just breaks, and we don't can identify an earlier change of material's behavior before. Fire resistant, it's not flammable. It's a brittle material, so with, say, the consequences of the brittle material being interesting for the engineering, it's complex for the engineering to be handled as a system. It's mainly silicon dioxide sand, the most material: calcium, sodium, bore, some aluminium, others being part of it, but it's 70 to 80% sand as material, which actually makes it also quite durable, quite sustainable as material, because it's yeah, a lot of sand, and it's good to be recycled as material as well. There are some processes to be used. The float process, the glass float process, developed by Pilkington. Sir Pilkington, who ended up in identifying the opportunity of having this float process. The raw material, the sand, is boiled, then within this oven being mixed and then brought on a thin surface. This thin surface has the strength of being liquid below the liquidization temperature of glass, and by that being liquid as air on top as well, which ends up on both sides liquid treatment to the material glass itself, which then ends up in a plant parallel surface as material. Then this process continues. We are now somewhere here. So this is, say, the floating process, the tin. Then this whole thing is rolled on a certain length, 600-meter length, cooled in the surfaces, scanned qua properties, and then cutted and transported and stored into this on the racks to be transported on the site. The dimension which we talk about is 2 meter, 3 meter 21 by 6 meter as a typical dimension. Alternative, the rolled glass, same liquid glass being pushed out of this nozzle and then rolled on a surface, which means there's this roll devices touch the kind of liquid glass, which gives it a certain pattern. So it's not plant parallel, not entirely transparent. That's one process. And the other process is this roll thing is rolled out. We actually can also fold it to create a certain U-shape dimension as a system. Then we go to the casting, the drawn glass process. Drawn glass process means you have the liquid glass and you actually dip something into it and then you take it off like honey. And by heating it, by bringing it up to the certain to the height, you cool it at the outside, and despite this cooling of the outside, we're able to create a very thin glass surface. It has some shiny surface, some um, um, wrinkles at the surface by being drawn, as I said, which is say a certain appearance of this. Casting glass means you boil the glass and you bring it into a die, and then this die is this mold is giving shape of the glass as a system. Extrusion process, you push a glass bar, a liquid glass bar through a nozzle, through a die to create a certain shape. I don't have a picture of that one. And then we have the blow and the pressure glass process. The blow and the pressure glass process, quite similar to each other. It's actually a glass drop which is brought in position and then by air pressure, either from the bottom or from the top, brought into the dimension, which is then the dimension you would like to get. So the blow process, as we see it here, with some air pressure brought into that, and then the pressed surface, which is actually a casting surface, an outer casting process, an outer surface, which defines the geometry of our components. Float glass left, cast glass, extruded glass, the glass tubes, no joint, extruded as one profile, and then the blow glass process, super cheap process. If it's industrialized, it could just go block, 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 as a dimension, as a system. These the glass is produced with 1600 degree. It's actually still liquid with 1100 degree, then brought into process, and then there are some opportunities, 3 ways to strengthen the material itself, to compress the material itself, and that's done by these heat strengthened glass processes. So the annealed glass, the simple glass, no additional treatment. It's just the material as it is, as it comes out of the float process. The heat strengthened glass, which is done in a way that the outside is the glass is heated to a certain dimension and then cooled at the outside very rapid. By cooling the outside very rapid, this compresses and then presses the entire body of the glass, so pre-stresses the body of the glass. And by then pre-stressing this body of the glass, the scratches at the surfaces are not that intensive, influencing the performance of the material, the performance of the glass. And by that it's say having a certain stronger appearance. It's named here being twice as strong as annealed glass. Naya, you can define it. And then the fully tempered glass is the same process, just faster to even create a more compressive stresses within the glass, and by that create an even stronger glass as a process. Post-processing, water jet cutting, so cutting surfaces, cutting edges. The typical milling does work as well. Edge finishing, so creating certain 45-degree angles for the glass edge. It's said that this increases the performance of the glass itself, glass strength, because of reducing the amount of scratches in the surface, which are always the starting point of the breakage of glass. Coating can be done. We have different types of coatings that could be brought on the glass, or we have acid etching, so creating different types of surfaces on the glass by acid being used. Then there's say the principal idea of how do we secure the glass by itself. Just adding another layer that makes the glass more secure system, because they have 2 pieces of glass which break and the one may hold the other if they're laminated. So the laminating of 2 sheets of glass is something very common which we are using a lot. When I go through the applications, it starts with the first pieces of cast glass being used in the greenhouses of the 1850s in the UK, mainly the UK, that's where they started. Then next level is single-layered glass, like we see in this very prominent architecturally prominent house by Mies van der Rohe. And then first, say, structural applications appear. I like this project a lot because it's one of the very few by Glasbau Hahn, a Frankfurt-based company, which, when you look at this, even at the top, have an eye section made out of glass, laminated glass. They developed a certain glue to laminate the glass in a good quality, structurally performative quality. And then this one, glass really getting into structural use. The first glass bridge made in in Rotterdam. Engineer was Rob Nice at that time. We see already the point fixing. That's a different story. If you go for the glass course, that's a different story, which is applied. Then we see the next level of advancedness using glass as a structural material, entire structural material. This is Apple Store 1. Now I think replaced with the second and the third one of this structure, and we see even changing the shape for the glass for the structural sake, so creating a deeper structure. By that, the glass not only acts as a flat surface, but allows to take more strength, like this one done by Rob Nice as engineer, another one by Rob Nice, which is casted glass bricks being stapled as a structure. So structurally speaking, this may be the least innovative, but material-wise speaking, creating all of these glass bricks and assembling them to each other, that's something which is super interesting to do. And by that, and this lecture about glass, again, the people which participated in this creation of